Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with learnbay.co. Happy learning!
Next module. So coming back to what is time series, it's numerical data. The difference is that this is recorded against time, and when we say time, it can be measured either hourly, daily, monthly, yearly, whatever intervals, right? But the important part is that the metric or the data point that we're trying to predict or forecast on has to be measured and against time. Now, what's the motivation behind doing this analysis is the understanding of the past, of course, trying to figure out what has been the movement of the number against time, and then using that understanding to forecast the future. So if you look at the philosophy behind the motivation, it does look like a supervised learning problem. So in a supervised learning problem, what you do is that you look at historical data, historical performance, and then you try to predict what's going to happen. So what we have over there is, if you allow me a second, I'll just get my note digital scratch pad out. It just helps if I am able to make small notes on the screen. So that should be helpful. But yeah, but we can carry on. So again, the main difference between time series and machine learning, and this is important to understand because sometimes I find people not being clear, and there are questions sometimes either in interviews or we land into debates. One such debate happened just a couple of days back, where one of our supervised learning models were being validated by a different team, and there was a question as to, okay, you want to predict or you want to forecast the product usage for the next 3 months or 4 months, or why have you not used time series? So it's important to understand the context and where time series should be applied and where not. Okay, all right, so let's get into that. So why is it different from other kind of data? Okay, it is different because because of this. Just keep in mind that this is what we are referring to. XT. What is X? X is what you're measuring. X can be any metric, production of a particular variety or a brand of car, if it's an automobile company, if it's a credit card company, spend on a particular, say, a particular co-brand card. If, say, for example, HDFC wants to know what's the spend on their Regalia card, it's quite popular. So that can be like, and if they want to record, of course, they do store the spend across time. That itself can be a time series, right? And it's something which is denoted as XT because we are trying to say that the value is driven by time. Like what we are essentially saying is that because it is January, the spend on the card is so and so. Because it is February, then the spend on the card would be 1 second. Yeah. So 40 million, say this is the spend. Had this been, say, March, this would have been. So we are basically saying that the time is like a feature, is like a independent variable, and it's driving the outcome. That is what it is. So you should also be familiar with this term called stochastic process. Is that a familiar term to most of you?
We've used it in stochastic gradient descent.
Okay. A stochastic process essentially is created when you have a variable or a metric which is guided by time, or it defines a certain distribution of data, basically a certain range of values or data over no, yeah, it is randomness, of course, that's right, but it is randomness. There is randomness, but the point is that it's measured across time. So a stochastic process can be, I'll give you a simple stochastic process. Say we're talking about number of buses between Whitefield Yeah, Mohan, go for it. What was your question? I would encourage all of you to use your microphone and just interrupt me and ask questions. That's perfectly okay. It is actually better to have an interactive session because that way, we are all on the same page and we get I would try to answer the questions to the best of my ability right away. So yeah, Mohan Barwal, you've raised your hand. Can you please go ahead? What's your question?
Yeah, actually, sorry. Yeah, it was a
No
mistake.
problem. No problem. Okay, by mistake, that's okay. But if you, whenever you have a question, guys, just go for it. Yeah, I'm perfectly all right with that. Is that clear to all of you? So that's how the sessions actually progress. So okay, let's figure this out. So what is so is a number of buses between Whitefield and Majestic, right? Uh, yeah, in a day, in a day, or say every hour. Yeah, or you might want to say that every 30 minutes. You see, I can measure the number of buses in different time intervals, but then what happens is the number of if the number of buses is say X, then it becomes a stochastic process and it is then driven by XT. So most of the time series data that you have are a result of some stochastic process or the other. Okay, so keep that in mind. Keep that in mind. The major difference between time series and machine learning, this is important to understand. What I'm going to do is going to try to create a new slide somewhere, and it will then probably give us something to write on. I guess we could do that here. Yeah. Okay. So what's happening here is that, say this is your data set. Okay. But it's a supervised learning data set. So you have customers here, cust ID here, and a number of items purchased over here. So you have 1, 2, 3, and 4. Okay. So you have 50, 45, say number of items purchased in a month from a store. Just making it up for you. Yeah. So if you look at what is happening here, this person buying 50 items is totally independent from this person buying 45 items. Understand this, guys. This is important. So if one person buys 50 items, it is not dependent on the second person buying 45 items. So this guy buying 3 items is totally independent of what 2 is doing. So what 4 is doing is totally independent of everybody, right? So there's a term called IID. It means independent and identically distributed. Okay, so we assume that in case of machine learning supervised models, data sets are IID. In case of supervised ML. Okay, what happens in case of time series is however different. Say number of buses, you're standing somewhere in this place called Marathalli. I know it's a pretty busy place. Okay, in Bangalore there's a flyover called Marathalli Bridge. So you this is standing there and you try to measure the number of buses coming every 30 minutes. So yesterday you minutes, so say for example 3 buses are appearing. Okay, now if 3 buses come in every 30 minutes, you can probably expect that kind of frequency to carry on. If say only 1 bus is able to come because of traffic and whatnot, then you can't expect that in the next 30 minutes 3 will come, or say 5 will come, right? You're probably going to expect either 2 will come maximum, or maybe 1 will continue to come. So you see what is happening based on your earlier observation. It has some relationship or some bearing on what you will observe next. Based on what you have observed already, your next observation will have some relationship, you know. Are you able to follow? So at t equal to 1, whatever you observe,
Yes.
t equal to 2 will be, so here's the deal, right? Let me just quickly write this here. T equal to 2 is driven by what happens at t equal to 1. That is not the case in case of supervised learning model, because we assume that every row is independent. So whatever the second row is capturing as a data, if I slice out second row and I just take the data, it is independent of what is happening in the first data. So the performance of second customer not dependent on the first customer, but the performance at time t equal to 2 is somewhat dependent on what you observe in t equal to 1. That is the fundamental difference between machine learning supervised models and time series. Okay. Um, right. So again, the larger time frames are actually good. In case of supervised model, we know that, you know, if you have a large sample set, then it is actually better for you. Large sample set is always better. Large samples in case of ML is actually always better, because you're able to you know, take a long-term view on the data and then come up with your estimates of and prediction. In case of time series, large time frame, in case of time series, it is not always better. I'm not saying that it is never better, but it is not always better. Can anybody think of an example? I'll give you one. So 2008, something terrible happened called credit crisis. Okay. So if you measure the number of people defaulting on loans back then, it would be much higher. So 2000, if you were to plot the data and say you will see 2008, right? Probably here. And then 2010, 2012, 2014, and so on till 2020, it would have probably, you know, tapered to some extent. Somewhere it probably is here, right? Now here's the deal. If I go back in time too much, right, and if I try to predict what's going to happen, say in the next 5 years, I may not actually, so I might get influenced by what happened in this time frame, 2007, 2008, and 2009, and it becomes a then this data signal actually might drive something, and I probably might overestimate what will happen in future. So it's not always better, but it's better because, you know, you get a long-term view. So stable activities are always better. So if you want to sort of figure out the popularity of, say, hatchback cars in India and how the sales have moved, you should actually take a long-term view. Only then you can try to see, you know, what's been the adoption of small cars and those kind of things. So so having it's, you know, it changes with time. Therefore, the bigger is not always going to be better. Okay, is that clear? What is the difference between a time series and supervised learning problem?
Yes.
It can come across as a question during interviews, that how will you sort of decide. And again, you know, just let me cover one more example. It may help you, because this came out in our discussion this week itself, and I just thought I'm going to probably talk about that in this session as well. Yeah, just a moment. I'm going to create another one. Okay. So if we go back to the earlier data or the earlier example, you might find, say I have data like this, cust ID, okay, C123. These are my data points. Okay. I'm sorry, these are my customers. And I have data against every month, their activity or engagement. Imagine that this is like a retail data. So this is a essential shopping activity or discretionary shopping items captured every month. My job is to forecast what's going to happen in May, and say May. Yeah. Okay. So as you can see, this data frame is a very typical machine learning supervised data frame. Okay. Isn't it? All of you will agree to this?
Yes.
Correct. Now, since I have to predict only 1 month, I have one option: treat this as my target, treat this as my independent, and get my job done. That is one option. The other option is, if you want to use time series, and this came up as a interesting point, is that just invert the data. How? I'll show you. So you just say that, Jan over here, Feb over here, March over here, and these are my customer IDs. So I had numbers like 40, 50, 60, 70, 80, 90, 100, 120, 140. So what happens is I now get the data sorry, I also had this, right? Yeah, 60, 80. I have 70 or 80 or 90 here, 120. Now the data is transformed. Now you might be wondering why I did this. Now this, if you see this is an independent time series. This is an independent time series. Now this is an independent time series. So this is probably time series 1. This is time series 2. This is time series 3. Now you can successfully apply time series, but you will essentially have to build separate models for separate customers and treat their performance individually. So did you?
Yeah, Aditya, so is it really realistic, this kind of approach? Because you can have multiple customers, right?
Yeah.
So
You
like,
can.
for example,
So
products also, you can have
yeah,
multiple. So
this is actually, this is the, I mean, if you have to convert, question is, if you say the question is, how would you convert a supervised learning problem? Yeah, excuse me for my handwriting, to a time series problem. So the answer is this. Okay, this is how you convert. Question is it feasible to actually sort of, get this done? And then, so was that Anupam?
yeah, yeah.
Yeah, hi Anupam. So to Anupam's point, what he's trying to say is that there are other factors also, like product, etc. So all of those, like I said earlier, in time series, you study one metric at a time. If say these are your spend data, spend in millions. This is spend in millions. You're only going to be concerned about spend, and you will ignore everything else. That is how a time series works. So if you have to bring multiple factors in, it will have to be done by a supervised learning. But if say you really don't care about products or anything else, you just want to use the past spend past spend values like this to predict the future spend. That's if that is the only thing you want to do, then you have two options. Either you can approach it from a machine learning perspective, or you can use it from a time series perspective. So you only concern yourself about the individual performance of the customer across time and the metric that you're studying. That is the only concern as of now. But it is not always practically possible. That is why we choose to, in these scenarios, we don't use a time series. In these scenarios, we therefore use a machine learning and a supervised learning data frame. So why I spend time doing this? Because I spent the last 2 days explaining to somebody that why did we not choose to do a time series. There were a lot of questions that, okay, this you can actually could have done this, and we had this debate, and I thought, since we're going to talk about time series, I might just well bring this to the session here. So I hope this gave you a glimpse of the kind of practical difficult questions that come to people. And
so basically, time series will negate all the factors which might come into picture when we are looking at the monthly spend of a customer, right?
It will not take into account other factors that might be driving the outcome. Yeah, that is how I would put it. So if the fourth month, so the spend in the third month can be influenced by many other things other than the spend in the last 3 months, right? So those drivers are not going to be considered by individual time series.
Yeah, but isn't that the case with ML as well? Because there might be some festive or some offers running or something like that, where
Yeah,
the spend might go up.
uh, well, see again, if you don't have the offer data, or if you don't have any, if you happen to just know that there are other factors influencing outside of the data, then it is a case with ML. But I'm assuming that you have information in the data. But if you don't have that information in the data, and you're just using the past spend to predict the future spend, then you have two options. You can either do ML or you can do time series. But this is it's a very difficult scenario. But my only purpose was to show you that if there is a question that is it possible to convert a machine learning problem into a time series problem, a supervised customer level problem into a time series problem. So this is one way to address it. So if you just look at this, right, we will be discussing something called moving average. Then we can come back to this example. You will see that moving average can be applied actually to come up with a forecast value, and then but then of course I am ignoring other things for like what is the tenure of the customer, how old is the customer in the system, how long has the customer been shopping with the business, how old is the business, how old is the store, if it's a retail store or if it's a credit card company, what kind of marketing offers are going on. So everything has to be negated. So in time series is just the metric that you're studying, and you're assuming that this the only reason why 40 becomes 50, 50 becomes 60, and 60 becomes 80 is because time is progressing. Time is progressing. That is the only reason the values are also changing. That's the assumption.
So the only feature we have is time, right?
Absolutely. Okay, so let's move on. So
Harit, I have a question.
mm-hmm.
Yes, so like you say, right, if you try to find out time series, so we don't consider other factors when we're trying to find out the time series. So suppose I give an example like expenditure, suppose expenditure only. It is not only depend upon the past, like what you already spent, also depend upon like this current year's suppose your salary is not hike, or or situation of COVID. So you are not. So there is also different factor which is also affecting the future spend. But why we are not considering this like
No,
time series?
I am not saying that you should not consider. All I'm saying is, unless you have data on it, you can't consider. Or just see from a purely from the hands-on analysis perspective, you can't. But of course, you know that because of COVID, say I look at 2019 data and I try to see, and I try to forecast 2020 data, right? I will be forecasting, cheerful numbers, but 2020 is not cheerful. 2020 is COVID affected for the whole world. So we know that the COVID assumptions have to come. If you observe 2019 data and try to come up with insights, you will not be able to get the COVID insights. Absolutely right. So those assumptions, those extra assumptions, you can apply after your forecast is made. So after your forecast is done, you can apply those additional outside assumptions to make sure the number becomes more relevant to the current scenario, economic context, or the business context. So that is a standard practice. So say, for example, you are planning for 2020. Okay, you want to figure out, okay, I want to set give my sales team some targets in 2020, and they would know how much business they should be driving. Now, in this case, you're not in a position to take 2020 data and just by the data come up with a good plan, because you don't know, because this data it's so badly affected by COVID that the numbers will go haywire if you do that, right? So how will you make sure that your forecast numbers are credible? So you're going to take some business assumptions, and you're absolutely right. Those will have to be considered, but outside of the time series analysis, with the purely from a analysis perspective, you can't really figure that out. But yeah, after your analysis is done, your forecast is made. So imagine this, like you've got to do it in two phases. First phase is just what statistics tells you. Just do that first. Second is what the current scenario is. Just apply those assumptions.
So Haritra, you means we find out first the forecast of 2020. Like suppose before I am spending like 10,000. So suppose time series forecast they'll spend next year 20,000. So after this forecast happened, we have to apply like current situation, some parameter we have to do manipulation on that first we have to do, like, right?
Yes, because see,
Is it like that?
Yeah, and yes, it is like that, and I'll explain why. Because within the time series algorithm, unless and until the past data, because unless you go to 2021, you cannot see the COVID affected data, right? Because the COVID affected data is in 2020. So if you happen to see the past year 2019, over there, no economic engagement data or no economic indicator will actually capture the impact of COVID. So that way, if you don't expose your algorithm to the history, it can't really forecast accordingly. So any models built this year is going to be badly affected. That's happening. That's actually taking place across the industry. Everybody across the industry, guys, they are coming up with assumptions. It is important to come up with assumptions, because otherwise what will happen is that you will not be able to come up with a credible business plan. You cannot really come up with a good forecast. Especially these are extremely they're extremely special scenarios, like Great Depression, for example, 1930s. You could not have predicted the interest rates accurately, but we know that interest rates can be predicted accurately. Even the movement of prices of certain commodities can to some degree be predicted accurately, but you can't do that in a depression scenario or a recession like this, like an economic downturn through COVID. So those kind of things, pandemic related problems can't be solved unless in the pandemic year you can't solve it. But you have to wait for the pandemic year to go away, wait for the past data to actually start showing what happened last year, and then when the past data showed, you can do that. Either you wait for 2020 to get over, but you can't always, because it's our job to come up with a forecast. So what we do is we come up with what we can from a statistical perspective and then apply assumptions. That is why we apply assumptions. Okay. Did I answer your question?
Yes.
All right. A couple of other people raised their hand. If you have any questions, go for it, please.
Yeah, can you quickly summarize in supervised and unsupervised how you use time series? Just summary.
So unsupervised, we don't use time series at all. In supervised, we don't use. But in a special case of supervised, when you're using limited data that is measured against time, and you're just using those as features to come up with what is going to happen or predict the next value. So you have two options to look at this problem, like a regression problem, where the last 3 months data, data point are your independent features, and the next month data is your dependent feature. You can look at it that way, or you can invert the problem. If you invert it, every customer will have its own time series, and then you can apply forecasting methodologies across columns. Over here, prediction will happen across rows. Over here, forecasting will happen across columns, if you just follow the direction of the arrows.
Supervised, we can use time series for regression or for categorical both classification section.
Classification, absolutely never. Time series is always numerical. It will not take values like 1 and 0. It is always going to be continuous. Okay. So classification, absolutely not. In a very special case of supervised, where you are only using a time measured set of features only to predict what is going to happen in the next time, only then. But say if you have stuff like customer tenure, and you want to use tenure, and you want to use product, okay, or say you want to use other things like satisfaction score or something like that, okay, so then you can't use time series. If you have to use these features, it has to be done using a supervised ML method. If it is just on time frames, if it is just on time dependent features, only then you can attempt to do it, but it is a cumbersome process. But there is a way to do it. I mean, if this question comes up in any of your interviews or discussions, you should be able to position it this way, that look, I mean, if you ask me to just use time captured features to predict what's going to happen in the next time frame, I can still attempt it by inverting the data and then treating individual customers, generating individual time series, and then applying forecasting methods. But if you would like me to include other features, for example, tenure, product, score, risk score, satisfaction score, and whatnot, then those things, if I have to consider from a business perspective, then I cannot use time series. It has to be done through a supervised ML. That's how you should be able to tackle the question.
But Arithro, like from ML perspective, like how will you classify this? Suppose if I'm using a hazard methodology or a survival kind of a thing, so it is a combination of both time series as well as a supervised kind of a classification problem, right? So like how will you classify that accordingly? Like, because that requires a time series also, right? You are measuring like whether survival is there over a period of time or not, whether the patient will survive over a period or not, or something like that,
Yeah.
So,
but over there also, the patient will survive over there or not. There are other factors also you are considering, right? Which are not time dependent, qualitative factors like the health of patient, the number of, so those things does not make it a time series problem.
Right.
If you just see, if you measure disease and mortality data, for example, if you measure the mortality rate of COVID, let's probably growth rate of COVID, I mean, that, or something like that, right? Which is essentially one single metric measured against time, then it's fine. But if you're looking at other factors like, okay, whether there were comorbidities, yes or no, did the person have diabetes, yes or no, and then that, because if you're using those features, it becomes a supervised learning problem. It cannot be a time series problem anymore.
Right. So it's a combination of both. Actually, you have the time series as
one
well as the
example
data.
is suppose the stock market data.
Yeah. So if you're just using the stock prices, and if you assume that the price is only driven by time, news in the market has nothing to do with it, company making profit has nothing to do with it, you have to negate every single factor and just assume that the stock is only a pure stochastic process measured against time. Only then you can use time series data to measure. So that's why, see, again, if stock price prediction against time had been the most accurate thing to do, I'm sure we would have had a lot more billionaires than what we have today. But it's not, because, from a statistical perspective, you can always predict for sure. But there are other factors that drive the stock prices, which the time series cannot take into account. The time series methodology does not take that into account.
Right.
Okay. So I hope it's somewhat clear to you. It may not be clear in one discussion. That's perfectly okay.
That means stock price is not like a time problem. It's a pure ML problem, right?
Okay. So I would encourage you not to classify problems into either time series and ML. Try to see what you're building and what kind of assumptions you are ready to work with. If you're trying to build a solution in which you have enough data so that you can use the stock price as a dependent variable, and you have a range of predictors. For example, how old is the company? How old is the business? How many times the shareholders were given dividend in the last 5 years? How many times the stock was split? If you have all those features and you want to use all those features, you have to ask yourself, do I want to use all those features? Because if you do, then it becomes a supervised learning problem. Now, if you decide not to use anything, just want to use the price, and you want to study the movement of price across time, and you want to predict the price movement against time just by looking at the movement of price against every month or every weekly price, whatever price movement you're interested in. So if you just want to consider the time movement of price, and then it becomes a time series problem. So there is, if you look at stock price as a concept, don't classify that into either a time series or an ML upfront. Ask yourself, what am I looking for? What am I comfortable with working on? If you're comfortable to work with only the time series, and that satisfies the assumptions that you're going to go ahead with, then it is a time series problem for you. And always, guys, whenever, so you guys, will always come across this problem. And actually, this is a great question. What's your name? I'm sorry, I didn't catch your name.
My name is Alok.
Alok, good question actually. So Alok, you've raised a good point. You will come across this a lot of times, that how do I classify a problem? Like, how do I link a problem to a methodology? But between the problem and the methodology, there lies the thought process. So you have to ask yourself, how do I want to structure the problem? That's where the main thought process of a data scientist should ideally come. It's a little less spoken about in data science circles. It's not that widely spoken about in machine learning circles. And in my discussions, I always try to emphasize on this, because I have noticed that when I started working, I obviously had a range of technical skills to get started. But then those were just that, technical skills. I basically knew that, okay, if I had to do this, then I'm going to apply this statistical method. If I had to do, so I just knew that. But then what I essentially was made to learn by my leaders, by my peers over the years, is that you've got to really think through and structure a problem. If you structure the problem, based on your structure, decide the method. Okay, so in ML also, there are n number of ways of doing classification, n number of ways of doing regression. So based on how you structure the problem, then you decide the methodology that you want to apply. So even in this case, for stock price, that's what I was trying to explain so far. That you have a way, you need to think of how do you want to build up the problem before you decide whether to use time series or ML. Is that fine, guys? Sorry, if it's not clear, we can probably come back to this. But
I just have a quick point to that, actually, related to the stock price only. So you can have a stock price to multiple companies. So each and every company, you need separate models, right? In this case, it cannot be as a uniform one model that predicts for each and every company.
Right? No. The Sensex figure. I mean,
yeah. It is supposed to be unique, but if you want to study them separately, but if you want to combine them and create an index, and you're studying maybe,
then it makes sense. Yeah, then it's okay.
But what I'm trying to, I hope that I'm able to drive home this point. It's an important point that you have to make sure that your problem structure guides you, rather than you decide the methodology just by the way the problem looks like. The problem might look like something, but is that something which is suited for the solution you're trying to build? That's where most of your thought process, and that is where our failures lie. I mean, I have failed enough number of times in my projects to actually confidently tell you that the answer lies in structuring. The answer actually lies in structuring. Even in the intercompany hackathons that we are doing, we typically, if people say that, okay, this is the algorithm that we've applied, the first thing I ask, or somebody who's judging would ask, is before we get there, can you please help us understand how did you set the problem up? What is your dependent variable? How much of independent are you going to use? Or what factors are you likely going to use? And then tell me how do you justify your methodology. So develop that process. I mean, it doesn't come overnight. It does take practice, but keep this in mind that this is a skill that you guys will have to develop over time. And I'm sure you'll get there. It's just about thinking. Just think a little bit more on the problems. Okay. So
one question, sorry.
All right. Okay.
While doing time series, is it only one function of time at a time? Can we have two functions of time at a time? Just like in the previous example, Jan, Feb, March, you have, suppose I have hourly also, one more function.
Okay.
Of time. So, to give an example, like I have a weather data, and from morning 8 to evening 6, I have some temperatures getting changed. That is one function of time. And Jan to December also, the weather, the temperature changes. It's a psychological. So, so I want to predict both the things at it. Means I want to take into consideration of both the times, hourly and yes.
I understood your problem. So the answer to your question is that it is as a best practice, develop separate time series model, predicting the hourly, predicting the monthly movement. Okay, and then try to see if based on say you predict the next month. Obviously, you will have 24 cross 30 hours, right? In the next month. So you will be predicting 24 cross 30 data points in the early time series, and you'll be predicting only one data point for the monthly time series, but they have to sync up. So either your forecasts add up to the total monthly number. If not, then you may have to take you can combine the forecast after you have built the individual time series. But as a best practice, always develop individual time series. Okay.
Yeah, thanks.
All right, cool. Great. Now, question is, what is it that we look for in a time series, right? I mean, we discussed about time series being a metric measure against time, and then, so what exactly are we looking for? So there are three things you're essentially looking for, okay? And these are basic points, easy to remember. If there is any discussion, you guys should be able to, talk about it. It's very simple. You're looking for overall direction. What is happening? Is it increasing or decreasing over time? What's the overall movement? Is there any growth or no? Like take the last point, take the first point. Do you see a movement upwards or a movement downwards? Or if not, it's a sideways movement. That is also fine. Yeah, Madhav, I'll just come to you. Let me just finish these 2 points. So inflection points. What is inflection point? Does it change direction at any point? So is it so that it was growing till a point and then it fell? Is it so that it was falling till a point and then it started growing back then? So what are some of those changes in direction? Third thing is that, is there any change in the growth? So if you see, in different industry data or different, say, commodity adoption data, I guess you could probably take the adoption data for Instagram. You might see that it did not grow initially because it was mostly, the use case was different. But over the last few years, the growth rate of Instagram has changed. So that is a third thing you are trying to basically check. That is in the rate of increase or the rate of decrease, has that changed from the starting point? So these are three main things you're looking for. What's the overall movement? Had there been a growth or no? Fine, there's been growth. Good. Is there an inflection point? Do I see some changes in direction? Like there is an overall growth I can see, but did the company face hardships in the paths to growth and it started falling up and then again it started growing? Or say, did the company have some, maybe a leadership change or a change in the business strategy, and it was initially not that good, but then they picked up? Like a typical case is Apple, right? So Jobs left, and then initially they were doing pretty well, and then after Jobs left, it wasn't that good, but when Jobs came back and they launched the iPhone, it really picked up. So you will see the sales data for Apple to show that kind of inflection points. The question is this, that you're also going to see if there is an improvement the time series is making in terms of growth rate increase or growth rate decrease. So is it growing faster or slower than it was before? So these are three things extremely important. So these are what motivates us to do the analysis. Yes, Madhava, your question. Madhav, your question.
I just lowered my hand. No questions. Sorry.
Oh, I see. Okay, no problem. Yeah, if you have some, please don't hesitate to ask. All right. So there are mostly three kinds of forecasting horizons: long term, 5 years plus. So long term capacity planning, or say, so long term R&D happening. So these are like mostly say government decisions. Or we used to have something called planning commission in India. So 5-year plans, things like that. You guys would have heard about it. So long term is one forecasting horizon. Second is like medium term. So 1 season to a couple of years. You're basically say planning a sales forecast for a couple of years. Okay, if I'm coming up with a facelift of say Hyundai Verna, and I want to make sure the facelift has a shelf life of 2 years, what am I going to forecast? So how many sales can I forecast? Based on the margin, can I forecast my profit? And if that looks a reasonable number, should I be investing my effort and resources into this, right? So things like that. So it's a medium term. Short term is like saying that, okay, I am more interested in figuring out what should be, say, or how many items should I have in my inventory for the next 6 months, or how much demand can I expect in the next within the next 1 year. So based on demand, so as I was saying, planning. So if you want to say create a target planning for your sales team for the next 1 year, you would want to do a short-term forecast just up to 1 year, and based on that you can try to see if you can assign reasonable sales targets. So three kinds of forecasting horizons. Long term, mostly long, you don't have to do. Short and medium term projects, they can come. Examples of time series data: monthly sale of Maggi Atta noodles from More Market, daily closing price of a stock, number of clicks on a website per minute, GDP of a country measured each year, downloads per minute of a music video. So simple examples, but just to drive home the point that time series, there are many things across our entire, I think the whole world of internet, where you can actually find a lot of time series data to work on. Almost anything can generate a time series data. And if the only thing is, do you want to use the data to look like, do you want to basically visualize the problem as a time series problem? Only then that data will be used as a time series data. For example, downloads per minute of a music video. You're just going to study the downloads per minute and probably forecast how many downloads can happen in the next 1 month, right? But over there, you're negating, you're not even looking at who is performing in the music video, what is the singer, what's the audio quality, where is it being shot. There are many other factors why people would download a music video. I'm not sure if you should be considering other things as well, like, popularity of the singer and all that. But that becomes a machine learning problem. But if you just look at the downloads per minute and you're interested in just doing that, then it is a time series problem. So again, visualization of the problem is extremely important for deciding which methodology to apply. Okay, so time series data presented mostly in a tabular format. So we find that this is an example, a simple example, where 2018, 2019 data is given. So you've got like 4 quarters. Against every quarter, you've got a sales volume given to us. It can be months also, can be weeks also, but yeah, essentially in a tabular format, in a structured manner, the data is captured. It can also be presented in the form of graphs. So and this is a better way, because that actually gives you a visual sense of how the numbers have moved. Now, if you go back to the 3 things we discussed, so can anybody tell me what are the 3 motivations?
The direction, if it is increasing or decreasing.
Direction.
Then changing points.
Changing points.
And then
ratio.
Then
slow increase and decrease.
Slow or fast. Slow or faster, increase or decrease. So let's see. What does this show? There has been a definite increase. I can see there is an increase for sure, right? This point is below, this point is up. So there is an increase, definitely. Changing points. Was it a steady increase? No, it's not a steady increase. Had it been a steady increase, the graph would have probably continued in this direction, correct? All of you with me?
Yes.
So there is a change in direction here. So it changed. The direction changed. The direction was here. There's a change. Then the change in direction was towards a downfall. Sales was falling. If this continued, then the graph would have continued like this. So that did not happen. There is another change in direction. Now again, if it had continued, it would have gone like that. It did not happen like that. There's another change in direction. So you can see that points of inflection marked in crosses are getting there. So these are things that we are interested in. We're trying to see where these points are, and I'll tell you as we progress through through the course, you'll see why these points of inflection are important, because we are going to talk about something called seasonality. You will see why it's like sort of important to sort of figure out why at which points do we see the curve change in direction. Then it's growth is slower and faster. So there are two phases of growth here, right? So this is one phase of growth, and the other phase of growth is this one. Question is, did it grow faster or did it grow slower? So how do you do that? You've got a couple of data points here. So you just measure the tan theta here, right? All you do is measure tan theta, you get the slope. But in reality, we don't measure tan theta, but I'm just explaining it to you because that's all that is, like the slope. So you're able to understand why it's tan theta? Did all of you understand?
Angle, because of the angle, yeah.
Yeah, because of the angle. But why does tan theta represent the slope? Is that something everybody understood? Yeah. Yes. So everyone got it right. Yes, dy by dx. Perfect. So dy by dx are dear old differentiation. Hello, guys. Am I still audible?
Yeah.
Okay. I think I lost you for a second because I'm a bit scared today, because I'll be honest. I mean, there was some issue with the microphone. I was not able to record, or I was speaking, but it wasn't getting translated into audio, and it took me some time to figure out. So I'm just checking. Okay. So we know that we are going to be concerned about the slope, changing direction, changing the direction, and then overall direction. Good. So far so good. Dotted points, and this is just another way of showing it in line graph, another way in which we can present time series data. So three ways: as a tabular form, a dotted line, and then a line graph. Okay. So now we have seen what a time series data looks like. What exactly is a time series? We have discussed at length as to why it's a different problem than a machine learning problem, although there are similarities between time series and machine learning problem. And we also discussed a special case where a machine learning problem can be successfully converted to a time series problem under very, very special circumstances where we ignore all the other factors. Now, when we look at a time series, right, what is it that it is made of? It's not just a data, of course, it's data point measured across time, but it can be broken down into 4 parts. The first part is called trend. Trend essentially is the overall direction. So the overall direction is trend. Second part is, I'm just going anti-clockwise here. So second part is season. Now, imagine that I have flexibility to define seasons however which way I want to in a 12-month time frame. Always remember, in a 12-month time frame, every season will occur once. Every season should occur once. That's the idea in a 12-month time frame. That's why our Indian calendars are actually a little bit better, because We have New Year's being celebrated according to our agricultural calendar. None of the seasons get repeated, but somehow it is winter in January and winter in December also. Ideally, that's the number of seasons are 2 in a normal calendar year. But what we say in case of time series is it happens just once a year. Okay, so it can be like every month is a season, every 2 months is a season, every quarter is a season, every you can say every 2 weeks is one season. So that's up to you. How do you define? So it depends really on the business problem. So if the business says that, okay, every quarter is to be taken as one season, then you basically define it like a quarter. Okay, now there's a random part in time series. Also, this is basically overall direction. These are seasonal, fluctuations. Then you have random. So this is something what we call as unmodelable or unpredictable part. It's COVID-19, for example. So this is like a random shock. So COVID, if you go to, when we go to 2021, guys, when we go to 2021 and we study 2020 data, this because of COVID-19, you will see some random shocks in the data, but you will see it only next year when you study, maybe you come across economic data. Then comes cyclicity. Cyclicity is nothing but long-term fluctuations. Okay, so is any questions on the 4 components? First component, trend, overall direction. Seasonality, seasonal fluctuations. What are seasons? Depends on the way the analyst defines a season. Can be quarterly, can be weekly, can be monthly. Every season occurs only once in a year's time. Then comes randomness. It's the unmodelable or unpredictable part. Then comes cyclicity. Cyclicity is a long-term fluctuation. So every, say, 5 years, you might see a change in direction, change in increasing or decreasing change in direction. Questions, anyone?
When time changes, both cyclic and seasonal are same.
So you have to combine a lot of seasons to call it a cycle. Like many summers will make a cycle, but a summer and a monsoon will be 2 seasons.
Okay.
Just we saw time series is supporting for a small time period. So how the fourth component is justified with them?
You mean how the cyclic component is justified, right?
Yeah, because we saw the time series is supporting a small time period for only.
Okay, first of all, brilliant question. And that is what I would have come to any which way. You will not find cyclicity in majority of the time series. If you're looking at last couple of years of data and you're trying to predict
what's happening. Can you please explain about that cyclical once again?
Sure, I'll do. So if you look at the last couple of last couple of years of data and you try to predict what's going to happen, say next year, you wouldn't find cyclicity. Cyclicity comes in a very, very long term. So every 5-year data, if you look at 5 years, say you're dealing with say 15 years of data. So you might find some cyclicity every 5 years that you can find. So how do I put it? I think even if you study Sensex data, right, for the last 15 to 20 years, you take 20 years. So every 5 years, you'll find some changes, cyclical movement in every 5 years based on economic cycles. Okay, so there was somebody who asked me to explain cyclical once again. So cyclical essentially is a combination of say multiple seasons and it's a long-term fluctuation. Okay, so this one, if I have to draw it, it would be like, say an increase like this and then going on, and then again an increase like this and then moving, and then an increase like this. This is probably seasonality. Every 3 months, you might see some spike and a fall. In case of cyclical, the graph will be very different, like that, you know. So you see this, like, you know, this point and this point covers one cycle. Long-term fluctuation. You will see an illustration later on. Yeah, you will see this as we go along. So components of time series, we're getting into the details of it now. Trend, patterns, directional movement of the data, overall or persistent long-term upward or downward movement. It's not always linear trend. It can be curvilinear, it can be quadratic, it can be polynomial, you know, depends on the kind of trend that you have. But depending on the kind of trend that you have, you will choose the kind of regression line you want to fit into, because here also the concept of regression is there, except that time is an independent variable. And always remember that you know, in case of time, say you have this one, right? So you're saying that at time equal to t equal to 0, in the beginning, the value of the metric was alpha, but in the next measured time, it increased by beta. So therefore, this is the growth rate. This is the slope and the growth rate also of the trend. Now comes seasonality.
As per the cyclic component, we can say like that time series is always work for the long period with the help of cyclic section, because for getting that cycle, we need to take a long term analysis period for 15 year, 20 year, 25 year. Am I right?
Yeah. Cyclical, yes, you're right, because cyclical, you know, is a long-term movement. So we'll just go through seasonality and then we'll quickly come to cyclicity. What is seasonality? It's, again, like I said, fluctuations, definitely fluctuations, periodic upward movement, downward movement that happens within the time frame. Typically, you know, it's driven by periodic usage, you know, these kind of fluctuations. So for example, if you want to say measure the sales of heaters or measure the sales of air conditioners, you'll see that during the summers there's a spike. During every winter there's a spike in the heaters, especially where I live, right, in Gurgaon, and these parts up north also. The heaters are important in the winters, especially for the months late December and mid January, that period. So it's very seasonal, periodic usage. It happens a lot, right? If there is a, say, you might find, I don't know, I think just a second, let me just think this through. Okay, yeah, use of mask, right? If you study the use of sanitizers, yeah, brilliant, right? Sanitizers have been in the market for a long time. I have been using a sanitizer, not always, of course, I'll be honest, but I got introduced to what a sanitizer is back in 2009 when HSBC had something outside of their bay, as people to just, you know, use that and come in. And we were joking that, yeah, it smells like alcohol, don't get too excited, right? So
Salarpur soft zone, I remember that.
right. So, but you know, it was like a fun thing. Nobody would actually go buy a sanitizer. I mean, like, who does that? It's being available in office. It's nice. It just smells nice fruity flavor and everything. But that was it. You know, I got introduced to then. But if you study the sale of sanitizers over time, you might find that during this 2020 time, it's really fluctuating a lot, right? So after April, it really shot up in India. After January, it shot up all over the world except India, but COVID had to hit before it actually happened. So some fluctuations like that, you can you know, think, not exactly seasonal because this is pandemic, not a good example, but I guess what I'm trying to say is that you might want to find where those fluctuations are happening, and then use those fluctuations to create some sort of index that will help you adjust your forecast, so that you're able to, in your forecast also, right, you're able to bring in those fluctuations, and that's important. We'll see how to do that.
Yeah, I think one better example is use of moisturizer that normally we used to use in
correct.
winter.
Yeah, moisturizers in the winter.
The seasonal uses.
Absolutely. Yeah. So typically treated as time series data analyzed to uncover trend. Okay. So there's an example where we can see at regular points, you have some fluctuations happening. These are all, seasonal fluctuations. Once you remove the seasonality, the graph will actually become much more smooth. It's something like this. So we will see it here. See, the graph is actually smooth. This is the same data, except that I removed the seasonality. So what I mean by that is, I did not get rid of this data point. It is there. This is the data point. Earlier it was here. Now it is here. Why? Because it got multiplied by a factor which actually removed it, and therefore we are saying that had there been no seasonal impact on the demand or the movement of sale, the seasonal impact on the sales, then it would have been here only. Now, because there is a seasonal demand, the data point has moved from here to here. This movement that has happened, if you follow my arrow, that's because there's a seasonal demand in sales.
So technically, how you will achieve this movement, because it's upwards, so you are making it come down to align to the next graph.
Okay. What is the question? So sorry, just want to make sure. What is the question?
So here you are removing seasonality and you are making a normal trend, right? So how are you achieving, on what basis? Like, so by seeing the graph, you know that these are seasonal points. So I want to get it down. So actually, what criteria you are applying here to bring to the down point? Like it's a bit up, right? So to align it, you have to bring it down, right? So so programmatically, technically, what logic you are applying here? So you are saying that you are not removing those.
No. Yeah.
So how are you achieving that actually?
Good questions. That is going to be there, discussed as a part of the module anyway. There's a certain way in which what we do is we do a seasonality index. We calculate a seasonality index. Okay, and then based on the index, we remove the seasonality from the data. I will show you how to do that. Okay, then comes the final component called the cyclical component. These are, periodic fluctuations excluding random component reveals phases of increase and decrease over a long period of time. That is the critical part. So it's a long-term product demand cycle, economic cycles in monetary and financial sectors. So you'll find that these fluctuations are taking place, but they're taking place over a long period of time. It's not going to happen in a very short term. So cyclicity, if you want to observe, you've got to give it a few years worth of data so that you cover a couple of economic cycles. If you want to observe the economic cycles data, you have to really look at a big range of data. So that's not always available to analysts. It's probably available more in research circles, but yeah, I can in case of government demand forecasting, etc. These guys do it. So people who are ISS, Indian Statistical Service people, they definitely work on cyclicity. Okay, yeah. So this is an example where you like this I showed earlier, long-term wave-like patterns, and it depends on one peak to the other. So this was one cycle. Then comes the irregular part. Irregular part are random in nature. They are noise because they are like nobody knows like what is the reason behind it. Nobody tries to attribute. So what happens is you look at a time series data, you take out the seasonality, you take out the trend, and then what you're left with is pure noise. Like that can't be modeled. That noise doesn't have any trend. It is just extreme randomness, and because of noise, it will get impacted. The final forecast will get impacted to some amount, but that's what we live with. We assume that there is a certain amount of noise in the data. Now, if going back to our earlier discussion of time series versus ML. Now, what if you want to model this noise? You will have to use other factors because the time series is not able to explain the noise. Okay, time series is not able to explain the noise. You've got to bring in other features. If you can, then probably you may try to explain the noise. For example, in the stock price movement, there's going to be noise in the time series for stock price movement. Why? Because the stock price is not just driven by time. There are other things. Positive news in the media, number of positive articles printed in the last 1 month, something like that, right? These are features. So those features will be impacting and what we observe as noise in time series, because time series is just essentially looking at the movement of the metric across a period of time, and that's what it is restricting itself to. Okay, so we look at what we call as we're going to perform a classical decomposition. So if you want to decompose a time series, there are 4 things you want to decompose: by trend, by seasonal effects, cycles, and then irregular component. Right. So how will it look like? So if you look at a time series data, imagine that this is your time series data. It does look extremely messy, and it does look like, there's no sense in the data, right? I mean, there is some sense that it is increasing, but we don't know what to do with it. So what we'll do is, once you decompose, this is what you are pretty much left with. First of all, first thing to notice is that there is no cyclicity. There is no cyclicity in this data because, there is no long-term fluctuation that you're observing. You're basically observing very close fluctuations up and down, up and down. Just a moment, guys. Just give me 1 second.
Hello. Yeah, hello.
Hi. Hello. Sorry, I had to just quickly adjust a couple of things. Are we, yeah, am I audible clearly?
Yes.
Okay. So as I was saying, there are, through classical decomposition, what we are trying to do is we are trying to make sense of the data. So the first thing we observed was that there is no cyclicity in the data. So what do we have left? We've got trend in the data. We've got seasonality in the data. And of course, we will have some randomness in the data. Now, once we look at the trend in the data, just the pure trend, this is what it will look like. Now, somebody was asking me a question on seasonal. How do we adjust for seasonality? Can I know your name, please?
Satish.
Hi, Satish. Thank you for the question. So, Satish, if you notice what we have here, these are indices. So these are first. So this is like somewhere in 0.94. Then the next season, it's a little bit higher, and so on. So these are the seasonal indices that we're talking about, and they're very close, very frequently occurring seasons. Okay. What is happening there is that you're going to take the original data and you will multiply this by the index. And once you do that, you're going to be left with, so this is just the pure trend. Okay. Just the pure trend. And then when you multiply this trend with the index, you start getting these fluctuations also in the data. But if you see this is now a seasonally adjusted data. It will be only more clear when we look at an example, but but that's in the next module, but we'll do that. Okay. When we think of a time series as components, and as a combination of components, it can be either multiplicative or additive. Yeah. So now in the multiplicative setting, we assume that the components themselves can be added up. The components themselves can be the components themselves can be multiplied, with regards to each of these. So if you calculate the trend component, calculate the trend component, the cyclical component and irregular, so it can all be brought together. Just one second. Okay, how did I identify it? There was a question. Let me show you how did I identify. So the fluctuations that you find, I think I did not catch your name correctly, sir. Okay, so Surendra, Surendra, can you hear me?
Satish.
Sorry.
Yeah, I can hear you.
Was the question from you, Satish, or something?
No, I can hear you. I can hear you. My question was from me, and I can hear you.
Oh, okay. I just wanted to make sure. Yeah. Okay. So yeah. So now what I'm saying is cyclicity. We know that it does not happen so frequently, right? So fluctuations. So here's the thing. It's a good question. Actually, it's a little bit confusing. So first thing is notice fluctuations. Do you have fluctuations?
Yes, we do.
Yes or no? Over here, yes, we do. Are the fluctuations frequent? Is the next question. So in this case, yes, it is frequent, right? Now we say that if yes, then cyclicity equal to no. You don't have long-term fluctuations. So you've got only short-term fluctuations in the data. You can use this argument as a rule of thumb to figure it out. I'm pretty sure none of you will ever work on a problem where you have cyclicity to deal with, because no business problem will actually go back like 20 years to figure out. Like American Express will never go back 20 years to figure out what was the spend back then and use that kind of trend to predict what's going to happen in the next couple of years. No, that doesn't happen. People are more comfortable using recent data. And as we look at a particular forecasting technique, we will see why it also makes sense. Surinder, did I answer your question, dude?
Yes, thanks. Thank you.
Okay, man. So, okay, we've seen this. Right, so we are at this stage where we're calling this as a multiplicative time series model. So we have the three trends. Now, if we imagine that you don't have cyclicity, if you have seasonality or you have both, so depending on whatever trend you have, right, they can be combined in a multiplicative fashion to create the value. And how do I put this into perspective? Say I take this value and I multiply it with this seasonal index to get this number. Trend, this is TI, this is SI, and then I multiply TI into SI. Unfortunately, there is an irregular component also, which cannot be ignored. TI multiplied by SI multiplied by this thing is actually YT, this data point. So, all of these can be multiplied to come up with one data point, because it's a multiplicative format that we are dealing with. Sometimes we have additive format also. So an additive format will be, TI plus CI plus SI plus irregular component. So this one, the example here is not an additive, it's mostly multiplicative. Okay, so we have come to the end of the model one, and what we have discussed is, we'll take a quick recap of what we have discussed. We'll keep the annotations. Do you want me to upload these PPTs are any which way uploaded from earlier discussions that I've had. If you want me to upload the one that we just annotated on, let me know, or I could just let you know where the other ones are. And a quick recap on what we have discussed, right? So we've discussed things like, what is a time series? Then we've discussed difference between time series, and machine learning. Then we've discussed, things like the components or time series. Sorry, these are not questions. And finally, the structural or classical decomposition. It is very likely that it may not have made full sense, but there is nothing to be alarmed. It doesn't make complete sense if you're hearing about time series for the first time in a single session. My recommendation is that you need to go back and maybe revisit these concepts again. What is important is that you start visualizing the time series the way I described, and it really will help you in a simple manner try to understand where we are coming from and where do we want to go, and practice all the time. So if you get your hands on any kind of data that you feel can be like used as a time series data, just try to practice the concepts we are going to subsequently discuss. Only then you will start building your expertise. So in the next module, what we will do is we can take a is everybody okay for a 5-6 minute break, if that's okay?
Yeah.
Yes.
Okay. So when we come back, we're going to talk about the following things. We'll start, we've done a quick recap, so we'll just skip that part. We will come and we will talk about a technique called moving average and exponential smoothing. Okay. We will also look at seasonality calculations. So that should answer your question a little better, Surendra. So that's coming up in module 2. So right after the break. Sorry.
10 minutes break, is it?
Is price of stocks having cyclicity? You may want to, Vinayak, hi, thanks for the question you asked. So if you're looking at, say, last 6 months data, year, 2 years, it won't have. But if you say study the company like Wipro, who has been around for a long time, like so if you go back to the 90s and check their data and then come back all the way to 2020, then you might find cyclicity. I don't know an answer per se, because I haven't really ever, I never really had the need to look at a time series data which is that big, which also has cyclicity. Okay, so we'll take a quick break. How will I identify what is multiplicative? It's okay. Don't worry about that for now. It's defined in that way. So if the values can be, so we'll come back to that later. So let's park that question for now. So we'll come back, guys, after 10 minutes, and then we'll resume our discussion further on module 2 of time series.
Thanks.
Okay. Hi guys, are we all here? Can we
Yeah.
start? Okay. So any is it okay so far? Any sort of questions or comments, discussions? All right. So we'll begin the model 2. This is a quick recap on the multiplicative time. We just discussed it, so we can probably skip this. So in my, there was a question on multiplicative cross additive. Now, most of the time series that you're going to work with are multiplicative. So we can essentially go, we can try to focus on what is multiplicative and how do we sort of how do we work on the multiplicative data. And the focus of this module for the balance of our session today is going to be on smoothing techniques. So how do we essentially iron out the fluctuations or the variations that we see in the overall picture of the time series? Okay, so that's where I'm coming from. Now, when we say smoothing techniques, primarily we will be talking about two specific techniques. One is moving average, right? Moving average, and the second one is exponential smoothing. In the next class, which is tomorrow, I will be covering other couple of, today we'll be covering simple exponential smoothing for sure. We will be doing other forms of exponential smoothing and, a little bit of what we call as ARIMA in time series. So auto regression and integrated moving average. So we'll try to look at that in the following class, which is tomorrow. Okay, so shall we begin? Does anybody have any fundamental questions on time series?
Yes, when we require the smoothing in time series.
Okay, we require the smoothing to iron out variations because we can't forecast the time series unless we understand the growth rate through trend, unless we understand the fluctuations of seasons by the seasonality calculations. We need to understand all of those things. Only then we can actually use forecasting methodologies and actually forecast. And we need smoothing techniques when we want to do forecasting.
Okay.
Okay. Now, calculating moving averages to get the overall impression of the pattern of the of the data and movement over time. Now, averages of consecutive time series values for chosen period of length L. Imagine that, okay, now you will now be able to relate to this example we discussed. I'm sorry. I'm just going to copy that slide here. Just give me one moment. I'll copy that and bring it to this discussion from the earlier module. The reason I'm doing it is because it will now be, you can start visualizing what we talked about then. Where am I? Yeah, this one. So we bring it somewhere. Somewhere here. Okay, so let's see what we mean by this. So what is the use of moving average? It is used for smoothing technique. It's a series of arithmetic means over time. The result is dependent upon the choice of L, length of period for computing means. So for a 3-year, if it's a yearly data, because if you look at, and I mentioned annual time series, over here I'm assuming that I'm taking the example of annual time series to explain to you. So if it's a yearly data and if it's a 3-year moving average you're calculating, then length equal to 3. If it's a monthly data and if it's a last 3 months you want to consider, the length is also going to be equal to 3, but it's months, not years in that case. Similarly, 5-year would be make L equal to 5 and so on. So computationally, it's very, very simple. Okay. It's just the question of taking the arithmetic mean over the last of the design of the desired length of time. So if it's 3 years, 3 months, 3 weeks, whatever. So if k is equal to 3, then it's just take the last 3 data points and divide by 3.
Yeah, here k equal to 3 means we are applying here k nearest neighbor.
No.
Okay.
The last 3 points, 1, 2, 3.
So how will choose that k equal to 3, k equal to 4, 5?
There is no method to choose actually. You've got to try 3, 4 different things to see which one gives you the better result.
Okay.
So try with 3, then go to 4, and then 5, and so on. Yeah, we will talk a little bit about k in just a bit. Okay, so over here, the last 3 data points we've been considered because k equal to 3 had, and the next moving average in the while k is equal to 3 is going to start from y2. So it's going to be y2, y3, and then the next point comes here y4. In any case, it will be 3 points and divided by 3 and so on, because k equal to 3. Okay. How does it look in the data? So you've got this data given to you. These are the 2 data points. So you can see that, this is a quarterly data. Every year, data is measured in quarters and it's given for some country, United Kingdom, and in this case, United Kingdom, but it's a quarterly data, and you're basically saying that you've measured the value against every quarter. So 4 values will be there to make up a total annual value. In this case, k equal to 3 meaning 3 quarters. Okay. And what you do, you take the average of it. So you see it becomes 13,642. Next 3, you take the average. Again, you take next 3 and so on. So this becomes your MA3. Okay. It's not that complicated to calculate. I mean, it's simple. The only thing is that because 3 is an odd point, 3 is an odd number. So where will you place the moving average, right? So the moving average needs to be placed in the middle point all the time. Therefore, you will have this value here.
Shouldn't it be at the 4th row?
No. That's because for odd values, you've got to place it always at the middle point. For even, we'll try to see how we do it. So this is now your new time series, right? So it's basically smoothened. So the smoothened time series should start just from 1 period ahead. So you're basically saying that, this is my value that my time series started with, but I want to just move 1 period and forecast. So it will be 3 moving average, and then this is the value.
So what like here for the Q4 will be the prediction for the Q4 99 will be based on the past records of Q1, Q2, Q3 of 99. So in that case, I'll be considering the moving average of all the 3 periods and then predict for the Q4 of 99, right? So moving average of all the 3 quarters like Q1, Q2, Q3 will be my prediction for the Q4 of 94.
For Q4 of 94?
99 Q4 99 Q4 will be the average of Q1, Q2, Q3 of 99. So that will be the moving average.
True. Yeah. So I mean, yes.
So I think you should the 3 whatever the column that you have added, it should be shifted by 2 more cells below.
No, it shouldn't be, because because I'll tell you, it's a standard practice to keep it. If it's odd numbers, you keep it at the center. So you can see that when we go here, right, when a 5-point moving average is created, then you will consider these 3 and then these 2, the moving average will correspond to this value. So the moving average value, the smoothened value, will be corresponding to this time frame.
Okay.
So it's again, so for Q4, what's happening here is the value that is coming here, again, don't think of them as forecast, because you actually have the actuals here. What you are interested to do is to smooth the value. So you are interested to have a smoother graph here, actually.
I just consider this as a naive forecasting, like without any trend periodicity considered. I'll just consider my past three records, average of the past three records as the prediction for this current period. So will that be okay if I say in that way?
I'm not sure if it's going to be okay. I don't have the answer to that question.
Okay.
So yeah, but what I can see is that these are all actual values, right? So you're predicting till this point, that's fine. Now what you do is
yeah, I'm having one question. If we try to plot this data in a graph manner, X and Y, and we start to plot a 1-1 data set as a United Kingdom 23,271. So how the graph flow is going on according to the time series we are capturing the 4 component?
yeah, you've got to let me actually show you. I would have shown you. Just allow me to go through this.
Okay.
So I'll now here the thing is keep in mind that moving averages are always centered with respect to the period that you're calculating. So if it's 3, then you're centering it with 2. If it's 5, then you're centering it with 3. If it's 7, then you're centering it with 4. Yeah, so that's how it functions that way. Now with regards
to that's the idea behind 3, 5, 7 odd number, is it?
Yeah, the odd numbers, it is easier to center, but for even numbers it's not that easy to center. Okay, so I'll come to that. Just let me just go through this. So you've got 5. If you have 5, then you can see the centering happening at 3 or the third data point. Now I haven't really, of course, I've just taken a part of the time series. If this carries on, you will see that this part of the time, this that's why we have this value. This is incorrectly pasted. Ideally it should end here, and this is coming because I basically pasted from the time series output. There are other values which is there in the time series, and the next moving average is this one. So it carries on like this, but it is always centered every single time. So you will see that for seasonal adjustments, having odd numbers don't help, because either we need it quarterly, we need monthly, or if it's a 12 every month there is a season, or every quarter, or every couple of months. It's more, it has to be like some sort of a even number that has to come in. Okay, now in that case, how do we center the moving average? So what we do is we calculate the moving average we basically center it halfway between t and t minus 1. To get a trend, we take the average of 2 successive estimates and estimate the halfway between t and t minus 1. So it is basically saying that, for k equal to 4, we take the first 4 values, we calculate one moving average. Then we take the next 4 values and we calculate. We basically take the average of these two. That becomes my centered moving average for k equal to 4. Because all moving average values must be centered. For all even numbers, it's a bit difficult, because it has to be done in couple of stages. First stage, you just take the first n number. What is n over here? So n is equal to 4 here, right? So you take the first n numbers, take the average. Now you take the next n numbers, you take the average. Now once you do that, you have 2 moving averages. Now once you have 2 moving averages, you're in a position to take the average of both of them together and create a centered moving average. This is what we call as a centered moving average. And this is only true when the length of time that you're dealing with happens to be even number. Okay, so stage one, if I think the value is 4 here, so we take uh, we can't really place, see this is not correctly centered because this is the first 2 values, these are the second 2 values, so I can't place a number here, right? So it is placed here just like that, it's incorrectly placed, but we'd still do that. Then we take the next number. Ultimately what happens is when we take the average of these two, we get this, and that's where it is. So it is basically I mean this is the centered moving average, but it is placed in the n-1th value, because we don't have any row in between 2 and 3 where we can place the data, but it has to be centered. Moving averages must be all centered all the time. Now once you look at the graph, what does it do to the graph? There was a question. So if you see the brown line, this is the original time series line. When you look at the moving average in stage 1 before centering, you can see that there are still some fluctuations there, just going like that. But if you look at the centered moving average, you can see you're almost capturing the trend. It is going like this. Very okay. Just a second. I think
I have a question. Can I ask?
Yes, please.
As we increase the k value, the k or n value which I'm mentioning, so the data is only shrinking, right? So if I increase the number of k in moving average, so are we not losing information from the data?
You're not. You're focusing on the wrong thing. Don't focus on the loss of data points like this. You're focusing on what is getting lost here, right?
Yeah.
You're not focusing on the values. Focus on the smoothness of the values. So the values actually start showing less and less fluctuation. So if you keep on increasing the length of time series, you will actually end up getting a smooth line. That is what you should be focusing on, because that is what we are trying to do. Obviously there will be loss, like we cannot have all the data points, but whatever we will be left with, it will be completely smoothened out, and that can be extrapolated to create a, so you can extrapolate this line much more confidently. You can fit a linear regression line, and that can actually give you a long-term trend, because this is what your trend is. You're uncovering your trend this way, so it goes on like that. Okay. So ideally, you're right, we are losing data points, but that is not a problem, because ultimately our objective is, I can lose data points, not a problem, but give me the essence, give me the smooth line, so that I can use that as much as possible smoothened line to uncover what is happening as a trend, and then extrapolate that to create a forecast.
Okay.
Does that help?
Yeah. So one more. Also, is there a problem of outliers, like an outlier here? Because now you see that when it took k is equal to 5, from 99 to 99 quarter 1 to quarter 4, the average came out to be around 13,000, right? And you see actually the average, the data point is at 23 for quarter 1 of 99. So the prediction for quarter 1 is having a lot of variance when you compare with this average value what you got. So how do we cater that?
In time series, we typically do not do any outlier removal. If there are outliers, if there are random shocks,
No, not outlier. I'm not saying outlier. I think that that may not be the right word to use.
Okay.
Because now, suppose say with this whatever data I have, I see that the average for 99 has come out to be around 13,000. But we see that the actual data point is varying around 23,000 for quarter 1. So if I'm using this model to predict for quarter 1 of 99, so I'm having a huge difference in the prediction, right?
So no, you will be. I haven't done. I am not. You have to let me finish.
Okay.
This is just the beginning. This is not all. This is just the beginning.
Okay. Apologies for that.
No, that's okay. You have. But here's the deal. It's a great question. It's the right question to have. But yeah, let me just go through the content and
Right, no problem.
you'll come to it. But here's what I want you guys to focus on. Based on whatever we have on this slide, just notice one thing, that these values, of course, the point that he made was absolutely right. You know, it has increased the variance. I mean, it has moved away from actuals. Agreed, it has moved away from actuals. Granted. But we don't know why these spikes are. What, we don't know what is the seasonality behind these spikes. We don't know that. And what is the randomness behind these spikes? We don't know that. What we know is that had there been no seasonality, had there been no randomness, then probably these values would be somewhere in this line. This is probably the trend. So this is uncovering just the trend part, and then we'll move on to the other things.
Okay.
Now, go back to the example, guys. We spoke about the fact that if you are restricting yourself to just using the last 3 months of spend data to predict what are you going to spend in the next 4th month, that is the only problem you're trying to solve. You're not going to be concerned about tenure, product satisfaction score, risk score, other things. Then you have the option of inverting the data and treating them as individual time series. Now that we discussed moving average, you can figure out that you now have the option of actually using moving average. So in the last 3 months, you basically look at last 3 months, you predict, okay, and then you carry on. You then again, last 3 months, you predict what's going to happen, and so on.
So here I'm having one doubt. So can I ask?
Yes, please go ahead.
For this concept, if we are getting a data like a January, February, March, according to time series 1, time series 2, time series 3, for that, if we are trying to plot a graph in X and Y axis, again, we got a data set like a January, February, March, and April. On that, we are trying to fit it out the linear regression. For that, again, the whole concept is arrive like errors, sum of residual errors, how to reduce the error and cost functions. So until and unless it's directly related with the machine learning.
No. Why? Okay, we are not discussing linear regression at all as a concept here. Don't forget about linear regression. Just take it out of your mind. Just for 1 minute.
Suppose confusion is continue.
Let me finish. You have a data set like this.
Yeah.
I have tied your hands. I have said you cannot use anything but last 3 months of spend data, and you can only predict using last 3 months of spend data what is going to happen in the 4th month. Okay. Or if you say that, okay, no, Aditya, I don't agree, I want to use last 5 months of data. I said, okay, that's up to you. But you can only use monthly spend data to tell me what's going to happen in the following month. That's all. You cannot use any other feature. So that's the kind of restriction you have. Now, once you convert this, once you invert the data, you then find out that, say you had 10 customers. So now you have 10 columns like this, right? Individual columns. So these individual columns are individual time series. So all I'm saying is you can use moving averages to forecast. You can use moving averages to forecast. I'm not talking about regression yet. Nothing else. Just
okay, but confusing from my end is if we are taking that moving average also and we are trying to plot a graph. So again, one month is using as a data point, and again it's plotted in a graph in X and Y axis. We are getting a lots of different points. For getting a best fit line over there, again we need to follow the concept of that sum of residuals, cost functions. Not like that.
No, it's not like that. Because
so how
you are getting confused, because I'll tell you why.
Yeah, tell me.
You are thinking that unless and until we fit a best fit line, we cannot forecast.
Yes.
I'm telling you, you already have your forecasted values. You already have it. You have it based on your moving average method. You have forecasted the values. Your job is done. So for the month of April, you already have forecasted a certain value based on the last 3 months average. That's what I'm trying to explain.
Okay.
So see, again, whenever you see a graph, I know whenever we see a graph,
yes,
we do fit a linear regression line. That is one method. That is not the only method. Okay, so there are other methods also. I'm trying to teach you moving average, which is basically a smoothing technique and a forecasting technique against time series, against time dependent data, which is time series data. So when you are using moving average, you no longer care about linear regression because your forecast values are with you. What will you use linear regression for?
Okay, suppose can you give me one example of the after getting the all moving average for Jan, Feb, March, April, May, how we segregate that point in a graph manner?
Fine, just plot it, right? So over here, right? So say this is 40, this is 50, this is 60, and you forecasted it's how much is this? 110 and plus 40, so 150 by 350. So you forecast a value called 50. So what you do is you then say this is what you're forecasting. Sorry, this is what you're forecasting, and this is your actuals.
Okay, so between this forecasting and actual, how we reduce that gap for getting a best accuracy according to the machine learning model?
You have to like over here. This is based on moving average, right?
Yes.
Is this the only method? No, we are going to talk about exponential smoothing. We are going to talk about other methods like ARIMA. So there are other methods also, right? You can choose which one gives you the best RMSE, root mean square error. You can choose the RMSE. RMSE is basically the root mean square error.
Yes. Again, for RMSE, again, I understand RMSE is there for that. My mind is going to again for that linear regression and for that best fit line.
But you don't have a dependent variable here. The only dependent variable is this one. The independent variable is time. So if you want,
there is a linear relationship between the one independent and one dependent.
Yeah. So okay, I'm a little confused myself now. What exactly is your question?
See, right now you showed me this graph after the moving average. We are plot the graph between y and x like this, and we are getting their moving average one. So as per you, there is a one independent and one dependent variable y and x means January, February, March, and the time series one data. There is a linear relationship between that. So according to that, if we are trying to get a best fit line, so that again we need to follow the machine learning concepts of linear regression, sum of residuals, cost functions, etc.
See, linear. So here's the thing I explained earlier also. So this is time series data. This is your intercept. This is your growth rate, and then this is the value t.
Yes.
The only thing is, if you can only think of it like this. So if you want to study the growth rate, you can do a plus bt, and we will use this. We will use this in exponential smoothing. But we are not. I'm trying to talk about a different technique. Okay, so you have to please allow me to finish the technique, and then
okay, no problem.
To exponential smoothing, you will see that I am using it. So just for your benefit, I'm going to show you. So we are actually not here, but in the next module, we will be using linear regression technique to figure out the slope or the growth rate. But that we will do. Okay.
Yeah, that's why my mind is going over there. I'm thinking something is there for calculating for RMS and all like that. So I'm right in track or I'm confused?
No, you are not incorrect. It's just that you're jumping.
Yes. Okay.
You're moving ahead of the topic being discussed.
Okay. Because when I saw January, February, March and time series 1, time series 2, time series 3, that time I got this point in my mind. So we can try to plot a graph. So again, that concept will be come here itself also.
The concept will come. You're not incorrect. The concept will come.
Okay.
But I am not talking about that concept right now. I'm talking about moving average. And I was just trying to show how moving average can be thought of as a method in that scenario.
Okay.
Okay, anybody else? Let's come back to moving average because that is the topic of the discussion. Kindly don't, let's just not jump techniques because it will be difficult for other people to follow. With regards to moving average, I think I should just proceed, otherwise it won't be that clear. So it is important to center the moving average. We saw that. Now the thing is, there was a question on seasonality. How are we capturing seasonality? Now over here, you see that YT represents the time series value. YT can be expressed as trend, cyclical, seasonal, and residuals multiplicative format. Now we have a moving average value. Moving average value basically can be thought of as T and C. If you subtract this, do the math there, you're left with just the seasonal component and the random component. The random component has no estimation. What we will do is we will use this relationship of the value of the time series and the value of moving average to calculate what we call as seasonal index. Okay, for each type of season, calculate the average of ratios, and then we have to do it step by step actually. So imagine that you have quarterly data given to you, 97 quarter 1 to quarter 4, 98, 99, 2000, 2001. And this is the hotel occupancy. There's some kind of index number given, okay? So I'm not sure exactly what it stands for, but it could be like an index number. What we are doing here is that we are taking centered moving average for, I think the period here is 4. That's why we are taking a centered moving average. So after centering, we are placing it on the third data point here. That's the best we can do, because we've seen this earlier also. I've shown moving average. So when we have k equal to 4, we place it on the center, the third data point of the original data. Now this one is centered. What we are going to do is we are going to divide the ratio. So we'll create YT by MA, and once we do that, we will have our indexes. So this column is not prepared just like that. So if you just see, the index for quarter 1 is 0.895. Every quarter 1 will have 0.895. Every quarter 1 will have it. Okay. Similarly, this is quarter 2. If you come to quarter 2 this year, 1998, again you find this same thing. Can you see? These are the indices. This is my quarter 3 index, and this is my quarter 4 index. Can all of you see that? Now, this column is not created just in one step. So I'll have to show you how to get that. This is the analysis of seasonality. This is where we are creating the index. We are actually going to see the calculation in the next slide. But let's go through that. We calculate something called quarterly ratios. How are we going to do that? If you see this ratio, y equal to MA, measured against quarter 3, 1997, quarter 3. This is where I'm starting from. So 1997, quarter 3 is this number. Similarly, in 1997, quarter 4, I have 0.81. In 1998, I have all the four quarterly ratios. 99, I have all the 4. 2000, I have all the 4. 2001, I have just 2. Because why? Because I have data till this point in time and I cannot go beyond that, right? So I have just 2 quarterly ratios. What is happening here is we are going to take an average of quarterly ratios across each quarter. So when I do that, I find the average of the ratios across all the quarters in quarter 1 comes out to be 0.889. In average of all the ratios in quarter 2 comes out to be 1, and 3 comes out to be this, okay, and 4 is this one, right? These are just simple averages. So when you sum it up, it comes up to be 3.974. Now you ask yourself a question that if there had been 3.974 seasons, if there were that, then quarter 1 index was 0.889. So basically you're saying that whatever trend value, whatever comes out as moving average forecast, right? You will have to multiply it with 0.0889. And this is where some of your, I'm sorry, I didn't catch your name. The person who asked the question earlier, about the regression. Can I?
Yeah,
Hello?
Kamal. Yeah,
Kamal.
Kamal.
Okay. So when you multiply it with seasonality, some of the gap will come down. Some of the error will go, or the cost function will start reducing. But the important question is this: If you add up, you get 3.974. If there were 3.974 seasons, then Q1 ratio is this, but you know that there are 4 seasons, right?
Yes.
So we will apply unitary method here, and we will simply say, okay, let me just do a simple calculation here. Let me do this calculation. Once you do that, you adjust this index for exact number of seasons you're dealing with, 4 seasons. So then it comes to 0.895 for the first quarter. Similarly, you're going to do this for Q2, Q3, Q4. When you do that, you will find that Q2 ratio slightly change. 090 becomes 098, 1.098, 889 becomes 895, 1137 becomes 144. But this is how it changes. If you had 3.9374, this was the index. But you know that you have 4, so you will apply unitary method to just divide that by 3.94. If you, in case of 1 season, multiply by the number of seasons, and you get the final index. That's how you get 0.895. What we should do is go back to the slide. Now understand what's happening. So you have all the indices calculated in the next slide. It comes back into this column, right? It again gets multiplied. So you can multiply this number and this number to see where you're like, I think, yeah. So you will essentially multiply the forecasted number with the indices to, sorry, you will multiply this one along with the index value to see where you net out. Yep. So if you do the math here, I think I don't have it calculated right away. I think just a second. Yeah. So if I multiply 0.642, see, if you look at 0.642, Kamal, the 0.642 and 0.752 are actually far away. This was your question. This was your question on the cost, right? But when you multiply it with the seasonality index, which is 1.144, then the number is 0.734. Now, can you see 734 and 752? These are actually not that far away.
Yes.
Can you see? Because this is your forecast, right? And your actual is basically going to be what? 7.752. So it's a little bit closer because of this, because you have taken into account the seasonality index and you've calculated. So what you guys should be focusing on is, and asking me is questions on how to, like, did this make sense? The seasonal calculation. This is where I would like to take a pause, not to take a break, but just to actually give you time to reflect on it and ask me the questions, because it may not be, it wasn't clear to me when I shared it for the first time. It took me time. So it is very much possible that it is not clear. You can ask me questions now in case you have questions tomorrow or next class.
I have a question.
Yes, please go ahead.
Can you just go back to the previous slide?
Previous slide, okay. Yeah.
So here you say that 0.642 is the moving average of one year data, right? 0.572, 752, and 534. And you're placing
last 3 quarters, last 4 quarters, yeah.
Last 4 quarters. So you are placing it at the third quarter here, 0.62. You said the average is placed as at the third quarter.
Third quarter, centering.
So then at the end, if you are going by that, this 0.703 should be placed at the third quarter of 2001, right? So because at the end, if we continue, we'll get 0.65, 0.785, 0.821, and one more data for fourth quarter.
No, but the data. Yeah, no. Yeah, go ahead. No, it won't be, because I'll tell you why. Because the data finished here.
Okay, so the last moving average, the last average 0.703 should be the average of 0.625, 0.785, 0.821, and I am not able to see the last data point there.
Yeah, it's actually a formatting challenge.
I mean, in true sense speaking, I should get one more data point here. So you said that either it should be a 5 moving average, or if it is 4 moving average, that is 4 quarter moving average, then a little bit confused there.
Did you understand the seasonality calculations?
Yeah, seasonality I understood.
Understood.
I was just confused with the moving average.
Okay. So the last three values, it's been a long time since I did the calculation, but I have to now manually calculate. If you just do the math yourself, so you'll probably.
So for the last, I mean, for the average of the last, the data point will be 0.625, 785, 821, and 630, right?
Mm-hmm.
And the average of that should be placed on the third quarter of 2001.
No. So okay, no, it's not that simple. You're forgetting there are two steps. This step can't be performed, right? You don't have this.
Okay, yeah, got it. Sorry.
You don't have this, right?
Yeah, I got it.
It's not there, right? So that's the issue. That's why you don't have it here. You would have had 1 point. No, you're right, and that's the right kind of thing to notice and ask. But the challenge is that this data doesn't exist, so the stage 2 calculation can't happen.
Yeah. So right.
Okay. So guys, any questions on the seasonality calculation?
I have a question. Regarding 4, right? So 4 you taken because of this 4 season.
Yeah, absolutely. So here's the thing, like I said, don't memorize the formulas. Don't memorize it. The problem with formula memorizing is that it will not stick with you. Concept will just go through. Understand this. You have 4 seasons that you know. Initially, there are 4 seasons, and that's why you are measuring the YT by MAT across quarters. If you want to define your seasons by months, you would have had 12 columns. Is that part clear?
Yes.
Okay. Quarters, 4 columns, month, 12 columns, weeks, 52 columns, but every season appears. How many times will a season come in a year, guys? Once. Perfect. Now that much is clear. Now this is one season. This is a second season. Just for simplicity, assume that these are seasons. Yeah. So now what you do is you calculate, basically arrange your data in the, you have to do this cross tabulation of time. This is your time. Do a cross tabulation across time and seasons. Okay. So once you do that, you are saying that across time, what is the average of the ratios in the same season? This much you get. Now, when you take the summation of all the averages, if they add up to 4, that is fine, but they don't add up to 4. They add up to 3.794. Okay. So you should ask yourself this question that, look, if I had 3.794 seasons, then I would have been satisfied with these indices, because my indices should explain all of the seasons. My indexes should explain all of the seasons. If it is explaining up to 3.974, that means I have to adjust the number in such a way that when I add up my indexes, they add up to the total number of seasons. With me so far?
Yes. Okay.
So again, when I add up all my indexes, they need to add up to my finally total number of seasons. Now that is the concept. You have to observe whether
can you please repeat from?
Okay. First of all, you know how many seasons you're dealing with. 12 seasons, 4 seasons, you already know that, right? Based on what you know about how many seasons, you have that many number of columns. In our example, we are dealing with a season every quarter. Therefore, we have 4 columns indicating 4 seasons. The time is on the y-axis. Here in this cross tabulation, the time is here. So across time, what we do is we look at the season, right? Every season, and sum up the indexes across every season. So we say that, we average out the indexes across every season. So we, on an average, season 1 is 0.889. On an average, season 2 is so and so, season 3 is so and so, season 4 is so and so. This much everybody understood, right? Yes or no? Yeah. Okay. Perfect. Now.
Yeah, I have one doubt.
You have a doubt? Yeah. Over here at this stage? Okay.
Yes.
Okay. Go on.
See, we know that we are going to break a seasonality between a four quarter 1, 2, 3, 4. If we are, and this is the also depend upon the business requirement. They want in a quarter base, they want in month base, they want in a week base. Am I right?
Business requirement, and also the understanding of the understanding of the nature of the business actually.
So
Right.
suppose we are considering seasonality for in a week perspective. So we know the week is sometime in a 52 and sometime in a 53. So in that time, how will tackle?
So again, like week, sometimes 52, 53. It depends on the year you're looking at.
Yes. So in that time, how do we analyze the time series? Because suppose in 2 year, 2020 and 2021, in between these 2 year, maybe week is for 52 and maybe week for 53. So between in these 252 to 53, there is a gap of the 7 days. So in this trend, in the manner of cyclic period and all in the time series concept, how do we overcome that condition?
So basically, you know, generally every week, if you have a season every week, it's almost never the case. You can have a season every maybe twice a month at the most granular level, but you don't have a season every week. So if you think of any sort of, even if you think of say games, they don't have a weekly per se, but they can have like a quarterly season, or they can at best have a monthly season. If it is the most frequent season you can have is like a fortnightly season, but these are unlikely scenarios. So having a weekly seasonality, I don't think you should be worried about it, because it's highly unlikely to have a business process with a weekly seasonality. That's
So
not
I have confused in my mind. We are talking about the seasonality, but we know if in a financial institution and banking sector, when we are trying to apply the time series according to suppose the credit and loan, for that one days also matter. So that is the difference between 52 to 53 week. Obviously, we need to focus on that 7 days whether we are lacking. That's the not a, concept of season and all. There is the matter of one day of the maturity tenure and all.
No, that is fine. You have a daily data again. So you have a daily data and you want to use the daily data to do the forecasting. That is fine. But even then, seasonal, when you define seasonality in your data, you are going to define it with a slightly longer duration than a week, even if it is for loan, etc., interest rates,
Yes.
etc. So you cannot say that um, um, it depends on the way the data set looks like. Also, you have to visualize the time series, and then there is no rule book per se that but really speaking, having a season every week sounds not correct to me. You can't have a season every week. You can have daily data for sure. You will have daily data and you will use that for forecasting, absolutely. But again, if you're how to use a daily data for forecasting, that is a slightly different topic. We will come to that, but we are currently focused on understanding how to calculate seasonality. If you have questions on understanding how to calculate seasonality, then that's fine. But otherwise, daily data, how to use daily data to do forecasting, and how does seasonality fit into there, we will come to that as a topic. But even when you think of seasonality fitting into the daily data format, seasonality will not be every week. It has to be with a slightly, you have to give a season enough time to show its effect, right? So if it's say admission time for the year, maybe May, June, July, education loans will go up. Education loans will go up. Right? But you won't find education loans increasing or decreasing every week, the application for education loans. So it really depends that you have to give it slightly more time to define a season. So effective definition of a season is given that every season occurs once a year, you can theoretically define a week also, but practically a week definition does not work, because every week, if you happen to have a season, then it is too complicated a scenario for anybody to manage. How can you manage a business with 52 seasons a year?
In fact, from loss forecasting perspective in risk world, like in banks, like you use quarterly data rather. So when you're talking from a time series perspective, like we do leverage a quarterly data rather than a daily data or anything of that sort, right? So even in scorecard also, when we are taking a negative bureau hit or anything of that sort, like it has to be a, you know, in the last 6 months, how many negative hits and all these things like that. So it's more of a quarterly kind of a phenomena rather than a daily thing in banks actually.
Right.
Yeah.
Was that Shubhadeep?
Yes.
Yeah. So, yeah, hi, how are you, man?
I'm fine. I'm good. Thank you, Aritra.
Yeah. So, yeah, so essentially, like, you know, seasons are mostly like quarters and months. But once we do that, once we like discuss and sort of decide a number of seasons, then we have this calculation across all the seasons. Is the last part of the calculation clear? Because this is where sometimes there are questions, and I do want to make sure I address those questions. So is the last part clear? We are bringing together all these indices, and we are not observing that it's accounting for all the seasons. So we are simply using unitary method to adjust for the number of seasons. That's all we are doing. We are saying that.
Yeah, so one like straightforward question is that suppose there is 12 month, then in case of 4, we will make it 12, right?
12, yeah.
That's what we are trying to do.
Yeah.
Okay. So yeah. So Aritra, one question is like you take 4 or 12. So what is the real? I want to ask you like what is the real impact in the season calculation? Is there a impact to take the number 4 or 12?
What do you mean impact?
Impact means I'll tell you when you try to calculate, right? Seasoning index, you try to calculate seasonal index. In terms of technically, like when you try to build a model. So what is the impact on performance of the model if you take less session or more session?
That is, you know, I don't have an answer. I haven't really seen it. You can maybe try to take this data. It's a picture though. You can try to check it yourself. But I explained over here that you have this moving average forecasted value. You multiply it with a seasonality, and you get something like a real forecasted value. What you do?
That's correct. I got it. I got it from the calculation wise. But I want to know that like theory wise, you change the different like number will be different. Then what is the impact? Okay, that is the first one I want to ask you. The second one is like moving average. Okay, so the first question is why you are using moving average means you try to smoothing the curve, right?
Yeah.
That's the reason you use the moving average, right? The question is why you want to smoothing the curve? Like what is the impact? That's what in that perspective I want to understand things.
Okay. So you want to smoothen the curve because you want to uncover what lies beneath all the noise and the seasonality. Okay. So if you look at these numbers, this number is 0.752. You have uncovered that mostly the trend to be like 0.642. Had there been no seasonality, the number could have been in this 0.642 visibility in the neighborhood. But you know there is seasonality, you calculated it. And when you multiply it, you could only get to 0.734. Even now, you are not actually at 0.752. There is some gap here. Now, this gap is the noise. So what you're trying to do is you're trying to make sure that you break apart a time series into components. Unless and until you break it apart, you would not uncover the underlying data pattern. The reason why you want to smooth the data is because you want to uncover the data pattern that lies beneath the noise, beneath the entire observed data, because the any time series data, it has randomness, it has seasonality. So you've got to remove those components and then only uncover the trend, and you can then see the true trend. And that is what you're going to use in order to create your future forecast. That is the motivation for doing moving average.
Okay. In that case, why should not we take the median? We make it average. We can take a median and it will be also better, right?
No, you're not going to use median. I'll tell you why. In median, Okay, let's use this example. You have say k equal to 3. What would be the median value? This value.
Yes.
So you're basically going to forecast with you're going to say that the next period forecast is exactly the same as a certain data point. So median in a time series format will pick up the exact actual value of a certain time point in the past. That will never be acceptable because that exact value is a result of randomness, it is a result of seasonality. So all of that will creep into your forecast. Your forecast will not be robust enough. You can't really it's basically saying that in the fourth quarter, whatever happened in quarter 2 will happen in the fourth quarter.
Okay.
That is the problem with median. But it's a good question, and I can recall that one of these projects we were doing supervised learning problem only. We are using monthly data, as I was showing in this slide. Where was that slide? Somewhere it was right over here. So we were trying to solve this. We were thinking of using median, but then we realized that it will correspond to a certain month, but then just one particular month's spend should not determine the fourth month spend. Rather, an average is a better method, because you have in an average you somehow have the influence of all the months together, but in median you lose out the influence of all the months. You just pick up one particular because it's the midpoint. Yeah. Okay. So all right, so I guess we've discussed this now. Now let's go to something called exponential smoothing. Okay. All right. First thing to notice is that in a simple moving average method, we've assigned equal weights 1 by k to all data points. So we haven't really said that the most recent data point is more important or less important than the other. We haven't made that kind of statement. We've just said that take a simple arithmetic mean. It's not even a weighted average. Just take a simple arithmetic mean, and there is no concept of weightage. It's equi-weighted. Even if you do sigma fx by sigma f, it's totally equi-weighted. Doesn't matter. The algebra will cancel out the f part from top, the numerator and the denominator. So it can be argued that it is often argued, and makes more sense, that recent observations provide more relevant information than the observations of the past. And why this is important is, again, going back, that time series only concerns with time. So observations of the past may look very, very different from the recent observations. Could be because of a lot of extra factors. There are often extra factors involved which a time series cannot capture actually. That's why recent observations are more reliable, involved in the remote past observations. Okay, so that you can't have access to, you don't have visibility into, therefore you're going to rely more on this thing. So what we want to do in this methodology is that we want to obtain a weighting scheme that assigns decreasing weights to more older observations, and the weights decrease in this manner, exponential series manner. First weight, most important, slightly less important, even less important, lesser important, lesser importance, extremely less important as we go back in time. Premise for exponential smoothing, we discussed this. Exponential smoothing give larger weights to more recent observations, and the weights decrease exponentially as the observations become more and more distant. Okay. These methods are more effective when parameters describing the time series are changing slowly. Most time series, most business processes actually change growth rates, or actually change slowly. The kind of growth that happened 20 years ago is not the kind of growth that happened in the last 5 years. Just look at the data volume in the world, right? The data volume typically, I think, trebled in the last 5-6 years, because that kind of growth never happened earlier. So the data capture itself should tell you something, that the fact that time series itself, is a concept which is heavily used in many circles, but most data points, most time series are going to change slowly over time. And that is where these kind of methods are most important, because you are observing, you're recognizing, you're attaching a lot of importance to more recent weights, more recent observations than the past observations. So this is a map I have built out. We will cover this one and this one in the second module, but over here we'll cover this. So if we don't have any trend and seasonal pattern, we'll use simple exponential smoothing method. Okay, so we now get into the method per se. So we are saying that is used for forecasting a time series when there is no trend or a seasonal pattern, but the mean of time series is slowly changing over time. So if you take average values of the time series, then say 24 months ago, or say 36 months ago, the average value was 24. In the last 6 months, the average value has probably become 29.5. It has moved. So there is some movement in the YT, but there is not a lot of movement in trend. So there is, like, if you uncover the trend, the trend is probably going to be like this. I mean, mostly flat, but a very, very slow movement. The slope is like really minimal. So tan theta is like almost almost zero. It is not there. So very, very slow movement, but we basically assume that there is no trend in the model. There is no trend in the data. So what is a no trend model looking like? So we are saying that let this be the time series value. Let this be, there is no growth rate. So let this be the intercept, and then this is just the random component. So that's what it is. So this is the mean level. We'll talk about how to get that. And this is something we can't remove. We can't really, we have to just live with the randomness. So step one, what we do is compute initial estimate of mean or level of time series at time period t equal to 0. Okay. So this is what we call as initial level. So L0, and depending on the time series given to us, we kind of do that. Then we compute the updated estimate by using a smoothing equation. The smoothing equation is the next level is going to be alpha times, alpha is a smoothing constant, so alpha times the given time series value plus 1 minus alpha, the last smooth level. My washing machine is going to keep beeping. Allow me just a second. I'm just going to shut it off. Yeah, just one.
Sure.
So where are we? Yeah. So we've got the initial level estimate by just the average of the values. Then we update that by using this relationship. You're saying that you take the smoothing constant, you apply it on the data given to you, then you say 1 minus alpha times the last level. So the next one, when you will see how it moves in exponential smoothing. So we will just explain that using algebra here. So we'll say that the next level is given by alpha yt plus 1 minus alpha lt minus 1. So what is L? This is the level of the time series. Or we say the level estimate of the time series. Okay. Now what will happen in LT minus 1? LT minus 1 can be substituted again with this formula. It's going to be alpha yt minus 1 plus 1 minus alpha LT minus 2. Right. So this becomes alpha yt, of course, was there, plus 1 minus alpha times alpha yt minus 1 plus 1 minus alpha square LT minus 2. So now LT minus 2 is weighted with 1 minus alpha square. Okay, so you can see the decay, exponential decay in the relationship here. So as we go on and on, all the way up to the initial estimate. So initial estimate is going to be 1 minus alpha to the power t L0. So this one will have the least amount of impact, and this value will have the most amount of impact. So if alpha is 0.1, so this is going to have the most amount of impact. The coefficients measuring the contributions of the observations decrease exponentially over time. The best way to understand this is, of course, with an example. Let's have a quick look at that. But before we get there, I'll tell you a little bit about how to sort of assess the model. So this is not new to you. You have the actual data, and then you have the forecasted data. So sum of squares of errors is something we calculate. We have SSE divided by t minus 1. So over here, there can be a question, and I'm going to ask that question to you guys. Why do we have t minus 1? What is minus 1? And why is it there? In the denominator. Yep. Anybody quickly?
It may be kind of correction given.
Nope.
Is it like whenever you calculate the time of t, have only t minus 1 data?
No. So we have lost 1 degree of freedom.
Yeah, degree of freedom.
Why did we lose it? By calculating L0 equal to, this is the calculation we did, right? We discussed it here.
Yes.
Now we have already estimated that, so we lost that degrees of freedom. That's why you have t minus 1. Okay, so does anybody know what degrees of freedom is? So again, if you have any questions coming your way during discussions, interviews, whatever, degrees of freedom, always simply say number of independent variates that make up a statistic. You may have questions on what is a statistic, but I'm not going to get into that detail. We will talk about that in probably next class, or if you have any questions, we'll talk about it offline, okay? But remember this definition, number of independent variates. So you lost 1 degree of freedom there because you've already estimated 1. That's why you have MSE equal to SSE divided by t minus 1. MSE is fine, but RMSE is nothing but root of that mean square error. And this is basically, essentially, that's how we calculate the RMSE actually. Okay, now point forecast made at time t, if you make the forecast say 1 period ahead, so it's t plus, it's 1 LT. So t plus p is given as LT. This is all what has happened in the last 3-4 slides is extremely confusing because there are so many symbols. Unless we put numbers, we put examples, this will not be clear. And that was even my problem when I was trying to learn this. Unless they actually look at an example, it's never going to be clear. So let's just get right into that. So we have a simple example of detergent demand, and hypothetically, there's a company called ABC Foods Company, and their monthly data is provided to me for 2 years actually, and product demand in tons. Okay, so this is what you have given in the data. Now, the plot of this data suggests that there is no trend. So we're going to use just the basic model here, beta 0 plus epsilon. That much is clear. Now comes the interesting part. You go back a couple of slides. How many data points do you have? 24 data points. Okay. What is the denominator here? Only 12. But okay, I'll be very honest, guys. There is absolutely no theoretical justification to this, but it's a rule of thumb. We always follow this. We use half the time series data given to me. In case of an odd period, it gets a little bit challenging. For that, you can remove 1 period and make it even to do your forecasting. But you will use half the data given to you to calculate L0. Only half. So use the first 12 months to calculate L0, and you get this number. Okay, It is a common practice to use initial estimates of exponential procedures by using half of the historical data. There is no, I mean, no math or any. It's a standard practice that we follow. Now, in step 2, what we do, we have L0 already given to me.
One question. In that data set, we have 24 data points. So if we have 36, then we'll use 18.
Yeah.
Okay.
So we have L0, which is 360.6667. Now we are going to set alpha at 0.1. Again, alpha settings, half of history. Just a moment, guys. Just one moment. Yeah, sorry. A setting of alpha and half of history. So these are mostly thumb rules. You know. So alpha, best alphas are 0.1, 0.2, and so on. So you remember that if alpha is 0.1, then you're basically going, the higher the value of alpha, the faster will be your decay. The faster will be decay, and the, that much less important is going to be your older observation. If you just go back to that algebra page that we had, yeah. So if the alpha value increases and it comes closer to 1, that much less important this becomes. Older value becomes. So you've got to try a little bit, iterate it and compare your RMSE values. That's what I normally try to do. So over here, we have L0. So L1 becomes alpha times Y1, which is 0.1 times 362. So you're taking just 10% of the recent observation, and you're taking 90% of just what happened in the just immediate past. Okay. And we're saying, okay, the next level is going to be this much. Secondly, the following level L2 is going to be alpha Y2 plus 1 minus alpha L1, and so on. So we have this sheet here. So this is a good way to set up your exponential smoothing spreadsheet. And in the next class, before we move, there are a couple of other things in Holt Winters and seasonal adjusted exponential smoothing. Before we get there, I'd like to spend a little bit of time, maybe the first 30 minutes, creating a spreadsheet like this, so that it becomes a slightly more hands-on for you guys from tomorrow. Okay, so let me go through this so that we are like all on the same page. Alpha here is 0.1. We know 24 data points are given to me. Okay, and SSE, MSE are formula driven, so don't worry about that right now. So L0 is calculated at here. So we say that even before time began, this was my level. What do we mean by that? So this is the scenario. So beta 0 is not dependent on time, right? So basically, if this is equal to t equal to 0, this is your beta 0 value, and then it goes on. Think of it like your intercept. So you should be okay with that, right? So this is your beta 0, just before the time series data even started to happen. Then forecast made last period. Basically, this is where we are updating the forecast values, using this 0.1362 plus 0.9, 360.6667. So 360.8 is going to be here. Yeah. So at every data point, you're going to like compare it with this. Sorry, wait a minute. No, my bad. At every data point, we are basically forecasting it like this. So we are here. This is my L0. This becomes my L1. This becomes my L2 and so on. My level 1 is 362 multiplied by 0.1 plus 1 minus 0.1, which is 90% of what happened just previous. So this becomes 360.8. So once we do that, we have to compare for error term, right? So for error term comparison, we will take the time, the data point against time, and we'll take the last period forecast and then compare the error. So 362 will be compared with 360.6667 and the error of 1.333 will come. Then you have squared error, of course. You sum it up, you create your SSE, you take the average by t minus 1. In this case, it will be 23. You get MSE, and then you finally get your RMSE. So depending on these values, so try to change alpha from 0.1 to say 0.15, 0.18, 2.0, 2.1. So just as you set your spreadsheet up, this will all be automated for you. So you can keep changing this number to see at which point you are minimizing your RMSE value, and then maybe stick to that. But the concept is quite simple. So this is how we are doing it. Essentially, you can see that. So compare these numbers, right, to these numbers. So they are not that far off. So this way, the number you can see in Excel sheet. I mean, I actually did this in the, but yeah, it's better that we reserve that discussion for tomorrow. Today just might be a little bit, little too much. I mean, there's a lot going on. So let me just pause there and see if you have any theoretical questions. You're likely to have questions. But when we look at the Excel implementation of this tomorrow, hands-on, it will be a lot more clear. But what we are saying is, at fundamental level, calculate your initial level based on half the values. Now, update your level, next level, by saying that, okay, my smoothing constant is 0.1 in this case. So it's alpha times yt plus 1 minus alpha times lt minus 1. So the next, if in case next level is L1, so it will be alpha times yt, nothing but alpha times y1 plus 1 minus alpha L0. When we substitute this formula, we then calculate the smoothed estimate. This is column second, the third column. The fourth column is we arrange the forecast in this way that essentially this period, it's the forecast to be made in the last period. So we then will compare that with against 362, the forecast was 360. Against 381, the forecast is 360.8, and 317, the forecast is 662, and so on. So that's how we will calculate the error and MSE and so on. So when you plot Y and you plot the forecasts, the column, second column and the fourth column, you'll see the values to be very, very close. And this is a better way of estimating than even moving average, because we are recognizing the importance of recent observations more than the older observations. And therefore, in the simple exponential smoothing, we don't really have to do much. We have to just follow 3 basic steps. Calculate L0, calculate your next levels using this formula, and you calculate your RMSE. That's it. But when it comes to other scenarios, like you go back to this flow chart here, you can see it here. When you have a linear trend, you have to do a regression. And that, I think it was Kamal, right? What was your name? There was a question on regression.
Yes, Kamal.
Yeah. So Kamal, you'll find me showing you how that we will bring in y equal to beta t plus alpha. Plus this will be here. Over here, not only you will get this, but also seasonality. Okay, so Holt Winters is also seasonality, and Holt's trend corrected exponential smoothing is something that will have regression coming in, because always remember, guys, that whenever we say trend, what do we mean? Meaning that it is time dependent.
Yes.
Okay, so in simple exponential smoothing, when we say it's beta 0 plus epsilon of course is the random part, right? But beta 0 does not depend on time. So we are recognizing and acknowledging the fact that the time series doesn't really have a trend, and but the level slowly changes over time, very, very slowly. So can't be called a super trend or a declining trend or something like that. Okay, so I hope you enjoyed time series module 1, mostly being theoretical, but it's foundational to understand the concepts and then move on to implementations. But I'm sure like by the end of the session, a couple of more sessions, you should be in a position to at least answer fundamental questions on time series. But trust me, expertise in time series takes a lot of time. It doesn't come overnight, and I have worked on time series, but not extensively because it doesn't need it. I don't need to work on mostly time series, mostly unsupervised and slightly unsupervised problems, but that's it. Uh, Time series, you will find people in investment banks like Goldman Sachs, Morgan Stanley, say Deutsche Bank, you know, the investment bank divisions, they will be like really, really working heavily on time series, financial forecasting. Those kind of people, those kind of profiles are more driven by time series skill sets. Okay, all right, so we are just on time. Yeah.
One question.
Mm-hmm.
You're taking like half of the data, right? So there is always possibility that you take one half of the data and the value is different from the other half of the data, right? You took suppose first 12 months. So for next 12 months also there will be different mean, right? Which value will be different.
Yes, it will be different. It may be, maybe not. I mean, we are assuming that it. So we are, like it said, right? There is no trend in the model. So ideally, they should not change. The mean should not change, but it is possible. We assume that it is possible that the mean is slowly changing over time. Slowly changing. The fact is slowly, meaning that there won't be a lot of change.
Okay.
Very slowly.
So that means we can apply only this like exponential things, and there is no trends. And
don't take away that concept. You can only apply simple exponential smoothing when there is no trend. You will apply Holt's trend corrected exponential smoothing when there is linear trend. You will apply Holt-Winters exponential smoothing when there is trend and seasonality both. This is the flowchart you have to keep in mind.
Okay. Got it.
Got it. Perfect.